is terminal velocity? If I jump out of a plane, which actually I have once, see if I can find a video of that.
In the door. Face forward. Across. Go.
I am going to accelerate. I'm going to get faster and faster and faster as I fall, as I plummet, as I descend towards this big ball of rock which we call our planet, the Earth. Now, eventually something's going to happen to my velocity. It's not going to get faster and faster and faster and increase like this. It's not going to do that because you know what? As I get faster, the forces upon me, the air friction, the air resistance, are actually going to increase as well. What we've got then is we've got this fixed force pulling me down towards the Earth. You can think of that as your weight or the force due to gravity on your mass. Now, as I fall faster and faster, my weight remains constant. My weight, as long as I'm on the same planet, as long as I don't just kind of mince off to Jupiter, is going to stay the same. My weight is going to stay at 9.81 times my mass. Now, as I fall faster and faster, the air resistance, the friction on my body is going to increase because, as we know from friction, the faster two things move against each other, the more friction there is. This friction opposes motion. Now, eventually what we find is that actually these two forces balance out. I'm going so fast now that the friction on me is so great that it actually equals my own weight. What happens when these two things are in balance? Well, guess what? I've reached terminal velocity. I'm no longer accelerating or decelerating. I'm traveling at a constant speed. And that is what people mean when they refer to terminal velocity. A graph to show what I've talked about looks like this. You can see the two axes here. My speed increases most drastically at the beginning of the graph. And then towards the middle of the graph, you can see that actually my speed is still increasing, but it's increasing at a slower rate. I.e., I'm still accelerating, but not as much as I was right at the beginning of the graph. As we go up, the gradient of the graph actually decreases until by the end of the graph, I've actually reached terminal velocity. I'm now not accelerating, I'm not decelerating, but my weight is totally balanced out with this friction force or upthrust or air resistance or combination of all three to equal my weight. I'm falling at a constant speed. Now that speed could be, for a human, it's around 60 or 80 miles per hour. If you're a peregrine falcon, that can get up to 150 upwards miles per hour downwards. All depends on the shape that you form when you're falling. You'll notice skydivers pull, they arch, and they count, they're making their body into a shape which is going to cause them as much friction as possible as they're falling, because they don't want to be traveling at 180 miles per hour downwards, because if you pull your parachute at that speed, you might find that your head comes off and your body stays where it was, so that's going to spoil your day. I hope that's cleared up. Terminal velocity is basically when the two forces acting upon you balance out and you're travelling at a constant speed. It doesn't just happen with skydivers, although this is the example we usually use. It can happen when you're dropping things into the sea. If I drop a rock into the ocean, for example, and allow it to sink down through the ocean, that object is going to reach terminal velocity very, very quickly, because the friction forces from the water and the upthrust from the water is much greater than you'd get in the air. Water is so much more dense, you get a lot more upthrust, so you're going to find reach terminal velocity much quicker. The graph would look something like this. I hope that's cleared up terminal velocity for you. This is Physics Friend. Don't forget to subscribe for new videos every first and third Monday of each month. And I hope you found this useful. Thanks for watching.